Hello everyone. In this lecture of induction motor, I am going to discuss about the determination of equivalent circuit parameters. Whatever parameter we have seen in our previous lecture, that description is also attached here in this video. So the parameter means we have to find the equivalent parameter by measuring the resistance, reactance, power, voltage, and current of supply. So by application of these values, we will be able to find the equivalent circuit parameter of an induction motor. So here measurement of DC resistance of a stator winding, we are going to find the equivalent resistance of DC resistance of a stator winding. Here it is connection is like that. This is induction motor, and here we are using to calculate the DC resistance value by considering the here R1 and R2. These two are connected in series, and the series equivalent, the measured value between the two terminal is equivalent to 2R. 2R1, R1 and R1 is here, so it will be equal to 2R1. Usually the bridge is used to measure the DC resistance. Bridge method, we know very well that method is used to measure the resistance of the stator winding. So here the DC resistance between these two terminal is given by VDC by IDC. If a stator is connected in a star, here it is shown, it is connected in a star. This connection is not done, so connected in a star. So now these two resistance are in series. So R1 is RDC equal to 2R1, and so RDC equal to 2R1, and using the relation means RDC equal to twice R1. So R1 will be equal to RDC by 2. And if the connection is connected in connection is used for delta connection, so we know that the equivalent resistance of the delta and a star relation, we know that resistance in delta equal to 3 times equivalent resistance in a star. So using this relation, so the delta a star resistance, we can put 3 into a star resistance is RDC by 2. So RDC by 2. So R delta, if connection is in delta, then this equivalent resistance will come. So this is shown here. Now determination of equivalent circuit parameter. We have to perform two tests here. That is the called a no load test. No load test means our machine. Here I am showing some diagram. Uh, I'm going to put all the diagrams. So here we can see very easily that this machine is running at no load. Load is not applied here. That means no load condition is there. So slip will be almost zero, because here if load is not applied, slip, as we know, ns minus nm divided by ns. And if no load applied, this motor speed is almost equal to the synchronous speed. If load is not applied, then this value becomes 0. So no load condition means slip is 0 here. A machine is running at synchronous speed. Here this is the voltmeter connected between two phases, and here supply is given to the stator, and this is three phase star connection. This wattmeter is used to measure the power losses, and ammeter is used to calculate the current. So in this case, we can see very easily that this voltage at no load means load is not applied here. This is the no load condition. So voltage will be VNL divided by per phase voltage. This voltmeter reading will be VNL by root 3. And I1 current in phase 1 will be same as the no load current, because it is connected in a star connection is here. So Z impedance, we know that impedance is voltage by current. So V1 is known by the reading of the voltmeter. I1 is also known by the reading of the ammeter. So here we can find the no load impedance. So no load impedance is calculated here. So same no load impedance is calculated by measuring the watt meter W1 watt meter measurement power is also known. So resistance I1 is also known from here by measuring the ammeter current. So resistance we can also find P1 by I1 square. So once resistance is known, impedance is known, we can also find the X no load reactance of the no load Z NL square minus R NL square. So by using this relation, Z NL is known from here, V1 and I1 is known, R NL is known from here. So X NL is reactance at no load is also known here. So rotational loss we can find by using this relation, how much rotational loss will be there, because we are not taking any output. So whatever input we are giving here, so all so it is going to be lost. So that is why this is called rotational loss, and this rotational loss is given by PNL no load power, that is measured by the wattmeter, minus 3I1 R 1 square. This is the resistance of each phase. So current is also known here by the measuring the ammeter, by seeing the ammeter reading. So this loss is called rotational loss. And here the P1 is P total by 3. We are considering here two phase loss, and PNL is the summation of two wattmeter reading W1 plus W2. It may be plus or it may be minus also. Sometime it may we have to subtract it, sometime we have to add it also. So now this the equivalent circuit of this diagram is given here. V1 is the our per phase voltage, I1 is the ammeter reading, RNL we have already calculated from here, and X1 NL, X1 is the reactance of the primary, and XM is the, this is the magnetizing component from here. Here XNL no load component is nothing but it is summation of X1 plus XM. So this is no load parameter we have measured from the giving the input supply to the stator side, and load is not connected to the motor. So this test is conducted to find the no load values of RNL, X1, XM, I1, and V1 is already we have seen by measuring the value of the voltmeter and ammeter. So these three parameters are calculated with the help of no load test. Another important test is that is called blocked rotor test. These two tests are very important to find the to find the induction motor equivalent parameters. So in this method we can see very easily that here what we are doing, it is a blocked rotor test. Means rotor is blocked, it is not allowed to run by putting external load on the rotor. The rotor is blocked and it is not allowed to run. Means a speed of the motor or rotor will be 0. So slip will be 1. Slip is ns minus n m divided by ns. So this portion is 0. So this is 0. So a slip will be 1. So at blocked rotor test, the slip becomes 1. And this rotor is mechanically blocked by applying a load on the motor. It is not allowed to run. And the same wattmeter and voltmeter reading here, ammeter, same arrangement is done here also as we have done in no load test. So in blocked rotor test, what will happen? Measured value VBL means blocked rotor voltage. This is here less voltage is applied here. Means rated voltage is not applied here. Single phase, it is less than the rated voltage is applied here, and IBL is the blocked rotor current here. Either this current is this is the blocked current, and power loss PBL will be again W1 plus W2 2 watt meter reading. We have to observe this reading. You will study this in your experiment also in laboratory. This can be verified very easily. So PBL is W1 plus W2. Now calculate the per phase values V1, I1, and P1 equal to P blocked by 3. We are considering per phase, so 3 is divided here. Now RBL, blocked rotor resistance. So P1 power measured divided by I1 square, and this blocked rotor is nothing but R1 plus R2 dash. This R2 dash is the resistance of the rotor referred to a stator side. This is the rotor resistance referred to the rotor side. So this total resistance is equal to the blocked rotor test, and V1 and I1 is known. So ZBL we can find blocked rotor impedance V1 by I1, and similarly XBL blocked rotor reactance X1 plus X2 dash. X2 dash is the rotor reactance referred to the stator side, and this relation ZBL square minus RBL square. So ZBL is known, RBL is also known, so XBL we can find, and it is customary to consider that these two values are almost equal. X1 plus X2 dash is equal. So this X1 plus X2 is equal. So X1 equal to X2 dash equal to XBL by 2. And here from this relation also we can find R 2 dash, which is equal to RBL minus R1. So here we have calculated these values, and this is called the impedance of the blocked rotor test. In same case, we have calculated the, in case of the transformer short circuit test we have performed. That test is almost equivalent to the block rotor test here, and the transformer we have calculated also no load test, that is also same as here, no load test already explained in previous slide. So these values we have calculated ZBL, and ZBL is equal to ZBL is equal to V1 by I1, and RBL is P1 by I1 square. Here the one more important part is the performed at less than performed at frequency which is 24%, 25%. So this blocked rotor test is performed to find the series parameter, like here R1 is the resistance of the stator, R2 is the R2 dash is the resistance of the rotor referred to a stator side. So these two values we have find. In fact, ZBL we have calculated. The important part is that performed at a lower voltage and frequency, 25% rated frequency, means this test is performed not at the rated voltage of from here. Rated voltage is not applied here, but below the rated voltage we are performing, and frequency is 25% of the rated frequency we are applying. Determination of equivalent circuit. Some of the observations we can see from this the main point is given here. If the test is conducted at frequency FBL, blocked rotor, lower than the rated frequency, then the value of reactance must be converted. So here reactance we know that 2 pi into F into L. If this frequency is the supply frequency, if this frequency is changed, then this reactance will be also changed. So suppose if we are performing some other frequency that is equal to S multiplied by F into L, so in this case we have to modify this reactance by multiplying. It is suppose x2 I am writing here, so it will be equal to S into X. This also has been explained in our previous videos. So this term we will find that we have to modify the reactance to be converted to rated frequency value by considering the reactance is proportional to frequency. This reactance is proportional to frequency. If frequency is changing, then reactance will also change. However, for normal motors less than 20 HP, the effect of frequency are negligible, and the blocked rotor test can be performed directly at rated frequency. So for a small rating of the motors like a 20 HP, we can directly give it to the supply frequency up to 50 Hertz. So in a laboratory, generally we are, and in our lab, generally we are using supply frequency. The reason is that the motor is of a small rating, means less than 20 HP. Some comment is here. The rotor equivalent resistance R2 dash plays an important role in the performance of induction machine. A more accurate determination of R2 dash is recommended by IEEE as follows. The recommendation of IEEE, whatever given, That will be follows in the next slide. Means we have to find the rotor resistance. R2 dash plays very important role that is being given here. So we can see here, this is some diagram that we can very easily see by seeing the equivalent circuit of the induction motor. The blocked rotor test RB resistance RBL is sum of R1 and equivalent resistance say R, which is the resistance of R2 dash JX2 dash in parallel with XM as shown. So here we see this is our X R2. Here here it is R2 dash, because R2 generally we are having a relation R2 dash by S, but for blocked rotor test what we have done, slip is equal to Nm minus Nr divided by Ns minus Nm divided by Ns. So for blocked rotor test, this value is 0. So slip here becomes 1. So this resistance R2 dash by S also becomes R2 dash. So this R2 dash is coming here. Now, that is why it is written R2 dash here. This is X2 dash. This is the rotor resistance referred to the stator side. And this is the XM part. So now we can see that these two parts, this and this, are in parallel. So we can find its equivalent. So we can find its equivalent means R2 dash plus JX2 dash are in parallel with XM, JXM. So its equivalent resistance we can find by just multiplying it, R2 dash plus JX2 dash into JXM divided by R2 dash plus JX2 dash plus JXM. So this is the equivalent resistance seen from this terminal. This is the equivalent resistance. Here it has a real part and imaginary part also. So we can do some mathematical manipulation here, and we can break this whole term in real and imaginary component. And after solving this, it has a real component, that is a real component R, and that value will come like this. If we break this real term by just rationalizing the numerator, just rationalizing the denominator, sorry, just rationalizing the denominator, so we get this value. Its real part we will get like this. So this is the called real part, and this is another part is imaginary part. R is calculated, that is given by here. You can solve this mathematical relation. That is not a difficult task, very simple task. So by doing this, we will get the real part of this equivalent resistance. The real part of this equivalent resistance is xm square divided by r2 dash square plus x2 dash plus xm whole square multiplied by r2 dash. This is R. And generally the case is that where R2 dash square is very small, that x2 dash plus xm whole square. So this is which is the case. So by considering this point, we can write R is, means this R2 is neglected here. So R2 dash square is neglected here. So the term remaining is xm square plus x2 dash plus xm whole square multiplied by R2 dash. And here from this relation we can write R2 dash is R multiplied by this term will come this side, and this equation, this is the more accurate value we will get by this simplifications. So in next part I will discuss one numerical problem based on whatever we have studied in this video.